right, folks, we have made it to our last definition of acid and bases, which is going to be the Lewis acid-base definition. And this is all about the donation and acceptance of an electron pair to form a brand new covalent bond, which we saw before in chapter 19 is called a coordinate covalent bond when forming complex ions, okay? And so a Lewis base is going to donate an electron pair, very similar to NH3 Iron Man like we saw before. Therefore, NH3 Iron Man can be considered a Bronsted-Lowry base and also a Lewis base. And as you can see, we still have that lone pair of electrons that's sitting out and hanging out. Every single Lewis base, similar to a Bronsted-Lowry base, also has to have that lone pair of electrons there. I'm trying to get a good color that shows it. There we go. And then the Lewis acid is going to accept an electron pair. So no longer are we saying accept protons anymore. We're now expanding our understanding of acids. It's not just about protons or that H plus or being able to have a proton in solution when mixed with water, like the Arrhenius definition. Now we're saying in general, Lewis acids are going to accept an electron pair. And so usually they usually have like a vacant orbital that's ready to accept the electron pair, and that makes it a little bit easier to form a brand new bond. Once a Lewis acid and base come together, they form what's called an acid-base adduct. And that is going to, this line is going to represent that brand new covalent bond that's formed, which again is called a coordinate covalent bond. Okay, we saw that before in chapter 19. So a tiny bit of review here. Also want to add that if the Lewis acid does not have a vacant orbital, a lot of times it should be able to rearrange its bonds. Like if it has a polar double bond, for example, it can rearrange bonds here as well to become a Lewis acid. So I just want to add that on. Now let's get into an example. Now we've seen NH3 Iron Man. We know he can act as a Lewis base in this example, but we have not seen a Lewis acid. And so our first example of a Lewis acid is going to be BF3 Loki. Yes, Loki is a villain, but he's basically cool, so I love to add him in here as well. And when I think of Loki, I'm like, okay, he's very cunning, manipulative in nature, and of course, he reminds me of a Lewis acid because he skillfully accepts an electron pair, okay? And as soon as he accepts an electron pair, you know that either an alliance or a scheme is coming along with it, all right? And so that alliance or scheme is being that coordinate covalent bond that's formed once that electron pair is accepted. That's kind of how I thought of BF3 Loki, all right? And then, of course, we have our NH3 Iron. Now, some folks might think, how are you going to connect Loki and Iron Man? And I'm not. I'm going to pretend we're in a what-if comic. So if you read comics and you know we're in the Marvel Universe, then a what-if comic is going to be an alternate reality or storyline for the comic book characters. So in this storyline, BF3 Loki actually forms an alliance with NH3 Iron Man. Dun, dun, dun. And when they form this alliance, because BF3 Loki is going to be a Lewis acid and NH3 Iron Man is a Lewis base, they're actually going to form a Lewis acid-base adduct. And as you see in the blue here, that represents that covalent bond that's formed between them. And now that they have an alliance, they can go forward and be super powerful and beat the heroes, right? And so that's one thing that we think of when we have what-if comics, and that's one way I kind of connect the information here. Another way to do this is just to visualize the reaction. So let me show you here. We have our BF3. This B, or boron, has the vacant orbital that can accept the electron pair from the nitrogen on our NH3 Iron Man, okay? And then once they go ahead and form the adduct, they're going to have a boron-nitrogen bond that's formed, and this entire thing is considered our Lewis adduct. A lot of times for us, we saw these as complex ions, and so say we had our complex ions that was formed here, okay, and then it had a charge attached to it, for example. So we still were looking at Lewis acids and bases even then. Now we're kind of saying, okay, now we're layering all the information together, and we've gotten down to the point where the Lewis acid-base definition basically are going to allow us to contribute to all of the previous definitions as well. So because Lewis acids are going to be the portion of this definition that really expands things for us, then we have to think of all the ways that an acid or a Lewis acid could be electron deficient. If it's electron deficient or has that vacant orbital, for example, it's going to have the ability to, again, accept an electron pair. So one example of our Lewis acids would be our three elements like boron and aluminum. And so as you can see, boron and aluminum both are going to have the ability to have that vacant orbital and, of course, accept an electron. And when they have the ability to accept an electron pair, you can see here, it's going to form the Lewis acid-base adduct. We also can see a lot of these group 3 elements like boron and aluminum form different Lewis acid-base adducts, and those adducts can go further to actually form organic compounds. So yes, some of these Lewis acids are actually used to form organic compounds, which is called organic synthesis, okay? And then if we go back before and just look at aluminum, we also know aluminum is small and highly charged. And so we definitely know it's going to be acidic in some kind of way just from previous definitions as well. Now we can see that aluminum is actually a Lewis acid too. And finally, molecules that contain polar multiple bonds also function as Lewis acids. So here we have SO2, here we have a double bond. This oxygen is going to donate its pair of electrons to this sulfur, therefore forming that coordinate covalent bond, right? And so that oxygen S bond here is formed. And then the proton that was on this oxygen is going to be donated to this oxygen here. So everyone still has its own octet. And so now we see an adduct that's formed, and that's another way that we can get a Lewis acid. Now we saw before how aluminum is going to act as a Lewis acid because it has that vacant orbital. But guess what, folks? It's also small and highly charged. And so it can be considered a metal cation that we saw before. And so hydration of a metal ion is actually a Lewis acid-based reaction. So we're going to take our metal, which is going to be small and charged. We're going to mix it with water, and it's going to form our adduct. Now, this is what we're used to seeing because from chapter 19, we're used to forming complex ions, right? Another example of a metal cation that we saw is going to be Fe-H2O6 3+ Mysterio. As you can see, the Fe3+ represents our small, highly charged metal cation, right? And then this entire thing is going to represent the Lewis acid-based adduct that has been formed. So you can essentially say a metal cation is going to act as a Lewis acid when it dissolves in water to form that hydrated ion, right? Or that Lewis acid-based adduct. And so we've definitely seen a lot so far. I do want to add a little bit of caveat of information that, of course, you won't have to know the details of, and we will get further into details of it as we go along in chapter 15. But guess what? Remember we were saying that most of the time we have a leveling effect with our Bronsted-Lowry acid and base definition from before. Now that we have a Lewis acid-base definition, guess what? That's not always going to be the case. So for example, we have nickel H2O6 2+, which is going to be a hydrated metal adduct, and we mix it with NH3, that NH3 is actually a stronger Lewis base than water. And because it's a stronger Lewis base than water, it's going to end up replacing water, forming a new adduct, nickel NH3 adduct, and of course, the equivalent amount of water left over. And the most equilibrium nature of all these acid-base reactions will be discussed further as we get into chapter 15. Now let's use our knowledge of Lewis acids and bases and go back to the Avengers compound for an example. All right, so this says identify the Lewis acids and Lewis bases in the following reactions. So again, we got to identify who's going to be accepting an electron pair and who's going to be donating an electron pair. Also, for Lewis bases, we must identify where the lone pair is going to be so we can verify that donation. And of course, for the Lewis acids, we must verify a vacancy so we can verify that they're going to accept an electron pair. Okay, so I kind of just called them out so I can have more space. So letter A, we have H+ and OH- is in equilibrium to form H2O. We need to figure out which one is going to accept electrons and which one is going to donate electrons. I don't know why, but my brain is going to acidic first, so I need to figure out all of the vacant orbitals or vacancies so that I can see who's going to accept any electrons, right? Okay, automatically I'm going to my boron here. I know this has to be a Lewis acid in some way because it has that open vacancy, right? Also, anything that has a plus value, you know, hey, you ain't got no electrons, so we definitely want to look at that. That means we have a acid here in H+, and we have a Lewis acid here in K+. So now, if I already know which ones are going to be my Lewis acids, that means the opposite are going to be the Lewis bases. So remember, we have to now look for lone pair electrons that can actually be donated to these Lewis acids. So here we know that we can donate lone pair electrons for our oxygen here. And then for our chlorine minus, we know we have the ability to donate electron pairs that is going to be surrounding it, okay? And so again, since this is Cl minus, that means it accepted one electron. And as you can see, it has 4 lone pairs surrounding it, so it definitely has some to contribute. And then of course, if we have water over here, then we also have our oxygen lone pairs that we can use, okay? So we have successfully identified all of our Lewis acids and bases just by circling. And so here, I would say the acid is the H+ if you want to write it out, and then the base is the OH-. That also would have been easy just by looking at H+ and OH-, but again, I wanted to use the definition. So some folks would be like, well, duh, H+ and OH-, we've seen this before. But again, use the definitions in these problems so it can be easier for you to remember them, right, when it comes time for an exam. So Cl- here is going to be the base, Has those lone pair electrons, and BCl3 is going to be the acid here, has a vacancy. Here we're going to have K plus is going to be the acid, and water is going to be the base because it is amphoteric. And in each example, yes, a Lewis acid-base adduct is formed. A lot of times, of course, they're not going to be writing all the coordinate covalent bonds or anything like that. We just see them as normal formulas, right? But just keep in mind that it is considered a Lewis acid-base adduct that is going to be formed. And this is how I would approach this question. So we've gotten through a lot when it comes to acids and bases, their definitions, and understanding. Next, we're going to go into a brief summary, and that'll pretty much wrap up chapter 14 for us.